Now you know how to design a reinforced concrete beam with unknown cross-section using ACI code. We are now going to take a look at how to design a reinforced concrete beam with known cross-section. That is, we already know the size of the beam. We already know the depth of the beam. We already know the width of the beam. All we need to determine is to calculate the area of steel that is going to be placed inside the beam. Now, the design process for a member with a known cross-section is a lot easier. When do we tend to design for beam with known cross-section? We tend to design for beam with no cross-section when we are using precast elements. That is when all of the formwork is ready made and all we have to do is start selecting some rebars. So this is when we are going to design for known cross-section. So let's first take a look at the procedures, because we need to know the procedures for known cross-section before we can design a beam with known cross-section. So the first step you are going to take is you are going to compute phantom moment on the beam. Now, when we design for unknown cross-section, we assume the phantom moment on the beam because we don't have the sizes of the beam, so we assume this. But for known cross-section, we don't need to make any assumption because we already know the size of the beam. So we can directly compute the phantom moment of the beam. So if the cross-section is known, the self-weight of the beam does not need to be assumed. So because we have the cross-section of this beam, so we don't need to assume the self-weight of the beam. We can automatically calculate the self-weight of the beam because we know the size of the beam. Now, the next step we are going to take is we are going to assume phi equals to 0.90. Phi is the strength reduction factor. So we are going to assume this in order for us to calculate Mn required. Remember, phi varies as a function of the strain in the steel. And if you don't know what the steel is, you have to make a guess because we don't know the reinforcement that is going to be placed inside the beam. So we need to assume phi to be 0.90. And the reason we assume phi to be 0.90 is because this is going to be in the tension zone. And we always want our beam to be tension controlled because when our beam tries to fail, it's going to give us some sort of warning that this beam is going to fail. So we always try to make our phi value to be 0.90 because this is in the tension control zone. So after calculating Mn required, the next step, which is step 3, we are going to calculate rho, which is the reinforcement required. If you remember, when we design for unknown cross-section, we make an assumption on the rho value, which we said rho is equals to 0.18 multiplied by Fc prime, that is the compressive strength of the concrete, then divided by Fy, which is the tensile strength of the steel. So we make an assumption on rho because we don't know the sizes of the beam. We don't know the size of the beam, so we make an assumption. But for known cross-section, we already know the size of the beam, so we can automatically calculate for rho required. So we can automatically calculate for rho, which is this formula. As you can see, we are going to use this formula to calculate for rho. And the rho value, this is a derived value, and we derive this value using the fundamental expression of beam capacity. The fundamental expression of beam capacity, which is Mn, which is the nominal moment required, this is equal to Fy multiply Bd square, then multiply by rho minus rho square multiply Fy, then divided by 1.7 Fc prime. So this is the formula for Mn. So using this formula, we derive rho required. So this is how we derive rho required using this formula. So after calculating rho required, the next step you want to take is, based on selected dimensions, you want to compute the required amount of tensile reinforcement. So you are going to calculate the area of steel. The area of steel is going to be rho design multiply B, then multiply D. B is the width of the beam, while D is the depth of the beam. Next step, which is step 5, we are now going to choose a reinforcement pattern that meets minimum beam requirement. So we are going to go to the beam design chart. We are going to pick a family of representation reinforcement pattern. Then we are going to pick one that is more economical. So using the beam design chart, we are going to pick a family of representative reinforcement pattern. Then we are going to pick one that is more economical. So we are going to keep the pattern as close to the area of steel required as possible in order for our design to be economical. Now the last step, which is step 6, we're now going to analyze the trial section to verify assumption. So we're going to analyze if this beam meets ACI requirements and if this beam have enough strength to withstand the load that is applied on the beam. So you need to know that phi mn should always be greater than mu. Phi mn, this is the factor resistance, while mu, this is the nominal resistance. So if phi mn is greater than mu, meaning our beam is safe. But if mu is greater than phi mn, our beam is not safe. We need to go back and select more area of steel in order for this beam to withstand the applied load. Or maybe we can change the tributary area of the beam, or we can maybe change the compressive strength of the concrete, or maybe we can change the depth of the beam or the width of the beam in order for phi mn to be greater than mu. So doing this, our beam is going to be safe and our beam is going to meet ACI requirements. So these are the procedures we are going to take when we want to design for beam with a known cross section. So in the next lesson, we are going to design a beam with a known cross section.